Let's consider an ideal system of n spin 1/2 particles. So let's say that we have capital N spin 1/2 particles in an ideal spin system. So we have non-interacting spins again. Now I call mu sub I the component along the up direction of the magnetic moment of the ith spin. So it is magnetic moment that is magnetic moment component, up component, for the ith spin. And I call capital M total magnetic moment, So if I go through all particles, they have magnetic moment mu1, mu2, second particle, etc., all the way up to the nth particle magnetic moment. Therefore, I will have for the total magnetic moment from I equals 1 to n mu sub I. And it is total magnetic moment in the up direction. Now if I take the mean of both sides, so if I go from here, take the mean of both sides, mean value of both sides, what would I find? The mean value of the total magnetic moment is I equals 1 to n mu sub I sum mean value, but it's the same thing as the summation I equals 1 to n mu sub I mean value. Why is that? Because if you take the average of two functions that are being added, you can also do average of one function plus the average of the other function. That is to say, averaging and summation commute. These two operations commute. So I can write this. Now, if this is an ideal spin system, there is no interaction between the spins, and the probability that any magnetic moment is up or down is the same. So there is no difference between different magnetic moments. So I would have, for the ideal spin system, I would simply have the average value of the magnetic moment of the first spin is equal to the average value of the magnetic moment of the second spin, and it's also the same for the nth spin. So if you do this summation, sum over I equals 1 to n mu sub I bar, you would get the total magnetic moment average is just the number of spins times the average moment per spin. And it's the same for all spins, because it's the ideal spin system. There is no difference. So this is basically what I have obtained here is the mean value of the total magnetic moment. If you do this per volume, then you would have mean value of magnetization. Okay, then I would like to start discussing the deviation of the total magnetic moment. Then we will have the deviation of the total magnetic moment is m minus m bar. So since m is I equals 1 to n summation mu sub I, the sum of all the magnetic moments along the up direction, minus sum over I equals 1 to n mu bar, which is the average value of the total magnetic moment. So this is simply I equals 1 to n summation mu sub I minus mu bar. So this is basically just the deviation for the ith spin, the magnetic moment of the ith spin deviation from the mean value is mu I minus mu I bar. So I'm going to get the deviation of the total magnetic moment from its mean value is given by summation I equals 1 to n deviation of the ith magnetic moment from its mean value. So this is what I will obtain, and so therefore I know deviation of m from its mean value m bar. Now, in order to calculate dispersion of m, I need to know the square of the deviation, delta m square. So let me write this explicitly, because this is deviation of the first moment from its average value plus that of the second moment plus all the way up to the nth moment. And this multiplied with itself, delta mu 1 plus delta mu 2 all the way up to the nth moment. So you can see that if you start doing this distribution of the product over the addition here, so you will get the first term will be delta mu 1 squared, so the second term will be delta mu 2 squared, etc. So I'm going to write these terms as delta mu 1 squared plus delta mu 2 squared plus all the way up to delta mu n squared. And then I will also get other types of terms, delta mu 1, delta mu 2, delta mu 1, delta mu 3, delta mu 1, delta mu n, etc. So the other types of terms I will have in the summation will be here, delta mu 1, delta mu 2, delta mu 1, delta mu 3, delta mu 1, delta mu n, and I continue. Then I would have delta mu 2, delta mu 1, delta mu 2, delta mu 3, and this will continue like this all the way up to the last term will be delta mu n, delta mu n minus 1. So I can write this using mathematical language for delta m square. I have the summation from I equals 1 to n delta mu I squared, so I have terms like this, and then I have summation I equals 1 to n, j equals 1 to n, I is not equal to j. I go through the terms like this, delta mu I multiplied by delta mu j. Okay, so this basically takes care of what I have observed here for delta m squared. Now what I need to do is take the average of this equation. So I take the average of delta m square. This is going to be summation I equals 1 to n. Remember, averaging and summation operations commute. So this will be delta mu I square bar plus I will have I equals 1 to n, j equals 1 to n, I is not equal to j. And also for statistically independent variables, the multiplication and averaging operations commute. So I can write this as delta mu I bar, delta mu j bar, since I have f times g, two functions of mu average is f bar times g bar for statistically independent spins. So I can write this. But this is just the deviation of mu average value. So for I is not equal to j, I have this delta mu I bar times delta mu j bar. Now if I calculate delta mu I bar, I would find mu I minus mu I bar average value. This is just mu I bar minus mu I bar, which is 0. Therefore, these terms will also give me a 0 here. So basically this part is going to give me nothing. It is 0. Now I continue with the remaining part of this equation. So I will have for delta m square average, the dispersion of the total magnetic moment is given by I equals 1 to n summation delta mu I square bar. And since I will have this value, delta mu 1 square bar, will be equal to delta mu 2 square bar will be equal to delta mu n square bar. Why is that? Because the probabilities for being up and down is the same for each magnetic moment. So it's going to be the same dispersion for each moment. So therefore I will have for delta m square bar n times, capital N times, delta mu square bar. So this is just delta mu square bar. It's the same number for each spin. So what I have calculated here is now dispersion of m, the total magnetic moment. Then I can calculate its standard deviation. So what is the standard deviation of the total magnetic moment? It will be square root of the dispersion, delta m square bar. So it will be square root of n times the standard deviation of the magnetic moment per spin. So I have this result for standard deviation. All right, standard deviation of m from its mean value. All right, so and also here in this equation, what I mean by standard deviation of mu is delta mu square bar average to the power 1/2, so square root of this. So what this means is that most capital M values lie in a range m bar plus or minus a standard deviation So that means it is equal to capital N times mu bar plus or minus square root of n times standard deviation of mu. Okay, so when mu bar is not equal to 0, I want to make a few observations here. When mu bar is not equal to 0, the average value of the total magnetic moment increases linearly with n, and at the same time the standard deviation of the total magnetic moment increases with square root of n. So what I call the relative magnitude of fluctuations in the m value, the relative magnitude of fluctuations, I can calculate to be the standard deviation of m divided by the average value of m, 1 over square root n standard deviation of mu divided by mu bar. So that's an important result. I see that fluctuations in the total magnetic moment around its average value will decrease with a factor 1 over square root n. So the more the particles, the less fluctuations around the average value of capital M. So let's summarize what we did here. So for an n spin 1/2 particle ideal spin system, I considered the magnetic moment up component of the ith spin mu sub I, and total magnetic moment is summation of all the moments. Now, if this is in an external magnetic field, if this is in a zero external magnetic field, right, we would have no preference for up and down directions. So the average value of the total magnetic moment would be 0 in that case. But if there is an external magnetic field, there would be a net up moment if the external field is up. Okay, so the total magnetic moment is the sum of all the up components of the magnetic moments. If I take the mean value of both sides, I see that the total magnetic moment is number of particles, n, capital N, times the average magnetic moment per particle. And this is the same for all particles because it's an ideal spin system. There is no interaction between the spins. The average moment value is the same. Now, if I calculate the deviation of the total magnetic moment from its mean value, I see that I will have basically the summation of over all the deviations of the ith magnetic moments from its mean value. And if I calculate the variance of the total magnetic moment, I see that I have two types of terms in the product of the summation of the all deviations. I have either terms like delta mu 1 square plus delta mu 2 square all the way up to delta mu n square, and plus I have terms, cross terms, delta mu 1, delta mu 2, etc. And this can be written as the summation I equals 1 to n delta mu I square, and summation I equals 1 to n j equals 1 to n I is not equal to j delta mu I delta mu j, because I equals j terms are in delta mu I square term. So if I take the average of this square of the deviation, I see that I would deal with the average of the deviations of each moment, which is 0, and then I would have the deviation, the square of the deviation of the ith moment average. So this would give me the dispersion for the ith moment. So I would see that the total magnetic moment dispersion is now n times the dispersion for each magnetic moment. And they are also the same because the probabilities for being up and down are the same for each magnetic moment. Standard deviation is square root of n times standard deviation of each magnetic moment, and therefore I would see that my total magnetic moment values would be in the range n, capital N times mu bar, plus or minus square root n times standard deviation of mu. And when mu bar is not equal to 0, when you increase the number of spins in the system, the total magnetic moment increases linearly with it, and also its fluctuation around its mean value, which is determined by the standard deviation of m, increases linearly with square root of m. So if I calculate the relative magnitude of the fluctuations, the average increases as n, the standard deviation increases at square root n, so the ratio is 1 over square root n, standard deviation divided by the average value. So as you increase the number of particles in the system, you will have less fluctuations around the mean value of the total magnetic moment, which scales with 1 over square root n.